Okay, welcome back. We are now on to the storage section of the information processing model. So remember, there is encoding, storage, and retrieval. We've gotten through the encoding section, which is all about how to get information into your memory. Now we're talking about storage. Storage specifically refers to the entire process by which you would get information into your brain, and that is really the retention of an experience over time. And there are three time durations for storage. The storage occurs over the course of tenths of seconds for sensory memory, about 30 to 60 seconds for short-term memory, and long-term memory storage can last for years, essentially for the rest of your life. Now, we've actually talked about these aspects because they overlap so much with the discussion of the information processing model and the time frame by which information resides in either the sensory memory, short-term memory, or long-term memory. So there's really not a whole lot to discuss about these things at the current time. After this, though, the issue of sensory memory is specifically geared toward things that are related to human language use. I've mentioned this earlier in the previous video. Iconic and echoic memory refer to specifically the sensory memory of either vision or of hearing. And iconic and echoic memories, they always show up in memory chapters, but there are as many sensory memory systems as there are sensory systems, which of course are the number of those are 6. But iconic and echoic, vision and hearing, always show up primarily because memory researchers focus on human language primarily in their research, and therefore their subjects are either reading language or listening to language, and so iconic and echoic show up as terms frequently in this area. There's nothing really especially important about them. They do show up. In fact, if you're not very careful, when you see the terms iconic and echoic, it may seem like they are different types of memory. But again, to be very specific about this, they are just the sensory memory components of either vision or hearing. And of course, there's a remaining 4 senses that are not identified here, simply because they are just generally not talked about. Now, in terms of storage, one of the components after our discussion here of sensory memory, we're moving on to short-term memory. Short-term memory, again, we're duplicating a little bit of the discussion that we had in the previous video. Short-term memory may be referred to as consciousness. To some degree, the idea of consciousness does not overlap 100% with short-term memory, but short-term memory and the processes connected to it do add up to a considerable amount of the aspects of consciousness. And remember, from the history of consciousness, consciousness as it was originally used in 1879 began to fall out of favor with the people that were pushing a scientific approach, and so they switched to the word awareness. Then from the word awareness, as that word became corrupted, they moved on to the word attention. And that occurred about the 1950s, and the word attention was primarily being used in the field of memory, and that's where the consciousness researchers kind of wound up going to, largely because after 70 years worth of scientific work on memory, the memory researchers had actually had a working model of a component of attention, and so it drew in a lot of the scientific interest from the people from the consciousness field. So certainly consciousness and memory overlap quite a bit, and what I always tell everyone is that since this time, since the 1950s until today, the field of memory has continued to expand and broaden its approach and explain more and more components of behavior, so that really probably no field more than memory has gobbled up the original questions about consciousness. And that's not to say that the field of memory has completely enveloped all the issues about consciousness, but it is the field that gives the greatest number of underlying scientific models to explain consciousness as opposed to any other area that's out there. One of the last terms, executive function, we don't go into too much here. You will see that a lot more if you take a memory course. Executive function is uh, really related to kind of the highest level of consciousness, or the most directed component of attention that you typically see. In terms of executive function, uh, it's oftentimes related to the master component of decision making that you are aware of in your own head. So the language is a little bit sloppy still, but if you want to say the little voice in your head that everybody claims to have, which is frequently associated with the primary attention you pay to a decision that you're going to make, that in terms of memory systems is frequently referred to as executive function. And it's not just another term to replace, you know, quote, the little voice in your head, unquote, but rather executive function follows a specific pattern. There's an underlying model in this case that's related to how decisions are made, how the behavior is carried out, the feedback system from the result of the behavior, and how that feeds back into your experience of how well your behavior actually functioned. So if you kind of think of it in terms of a three-term contingency, that there's an event that you have to address, you behave in some way, then there's a consequence, and your conscious awareness of the entire process is to some degree referred to as executive function. It definitely overlaps with attention. It definitely overlaps with the three-term contingency from operant conditioning. It gets a bit beyond what we can do here in a general psychology course, but it is a term that I put out there so that you're at least somewhat familiar with it. And if you take a memory course, you're almost certainly going to wind up discussing it in a lot more detail. Now, short-term memory is most certainly the place where active memories are processed. We've actually spent a considerable amount of time in the other video about that regarding the activation of rehearsal and how information is held in short-term memory for lengthy periods of time, at which point, through some underlying biological process that is not fully understood, partially understood, not fully understood, the memories in short-term memory will start to turn into long-term memories, which then no longer have to be activated with rehearsal, but instead will be retained as a result of biological change in your brain, and your consciousness could be focused on other tasks and then go back and then retrieve that memory even though you had not been actively thinking about it for some period of time. Of course, short-term memory, we've talked about this, decays over about a 30-second period. I don't think there's any more reason to talk about that. I think I beat that one to death in the previous video. But there is one new piece of information here, and that is when you evaluate how much information can actually be stored in short-term memory, there is a reasonable answer to that question. And the answer is 7. 7 plus or minus 2 being the most standard range around the typical average you see in the general population. So that is, if you randomly grab anybody from society and you evaluate how many items they can hold in short-term memory, the answer is about 7, plus or minus 2, so anywhere from 5 up to about 9. Now, Funny thing about the 7 items that you can hold in short-term memory, because that clearly does not sound like enough. Most people think that they can hold a lot more information in their short-term memory than 7 items, and in some way you actually can, but it comes as a result of the way you subdivide the information that's in your conscious awareness. So, for example, your short-term memory can hold 7 items, but any one of those items can then be further subdivided into 7 units. And each one of those 7 units can be subdivided into 7 units. And each one of those 7 units could be subdivided into 7 units, so on and so on and so on. So, in fact, I don't believe I've ever heard of any research which identified the number of times you can subdivide a single unit into 7 new components and then subdivide that further, so on and so on. So it seems, if you try to imagine, you can only hold 7 items in short-term memory. It doesn't really matter what layer of information it actually is. It's just that you're juggling 7 things at one time. And so you can always take one of them and break it into, at most, 7 items, and then deal with that information, and then you can go back up in the tree or further down in the tree to the level you need, but still always managing about 7 items at any one time. This moves us on to a clicker question. And this one is definitely a throwback to the States of Consciousness chapter where we spent most of our time on sleeping and dreaming. When you're asleep and dreaming, which components of the information processing model are functioning? And to give you a little more context about this question, you might remember, and I hope you do, that when we talked about sleeping and dreaming, I told you that when you're asleep and unconscious, you don't form long-term memories. And so if you dream for 45 continuous minutes and then you wake up right at the very end of that dream, you're only going to remember at most the last single minute of that 45-minute dream. So take a look at the answers. I'll give you a moment. You can pause the video if you want, and I'll give you the answer in a moment. So when you're asleep and dreaming, the components of the information processing model that are functioning is E, sensory and short. And it's important to recognize that, and I'm going to flip back here for clarity to the model, because when you take a look at this model, remember that the model always travels from left to right. A stimulus has to come in, run through the sensory register, then get this short-term memory, and then only if information is held in rehearsal in short-term memory for a lengthy period of time, it will then form a long-term memory. If there's no rehearsal active during the time that you're unconscious and dreaming, which of course there is not, because you don't speak to yourself when you're dreaming, or you're unconscious, you don't repeat things to yourself, you cannot form a long-term memory. So the short-term memory component is definitely working, but to get the short-term memory, you have to get through the sensory register. And so it's sensory and short that are both active and relevant components in this particular case. Sensory and short. Now, in terms of long-term memory, right? Now we've done sensory, short-term, and now long-term memory. Long-term memory is considered permanent storage. Once a memory is formed in a long-term memory, it can be with you for the rest of your life. Okay, and of course there is no longer time relevant for you than the rest of your own life. But long-term memories can degrade during the time that you have them. In fact, some of them, which are clearly long-term memories, may disappear under a day. So for example, if you drive downtown, you park your car somewhere, and then you go off, you conduct some business, you go to a coffee store, you come back 3 hours later, you remember where you parked your car after 3 hours. Now, because that memory was in your brain for 3 hours, that clearly constitutes a long-term memory, right? It's because it's certainly outside the range of the second duration of a sensory memory or the 30 seconds of a short-term memory. It has gotten well beyond that point. If you hold a memory for 3 hours, it is clearly a long-term memory. Having got your car and noticing that there's nothing strange, nobody keyed your car, tire didn't go flat, the car starts up fine, you're able to drive off. The fact that you parked where you parked is completely irrelevant to your life anymore. You very well may forget where you parked your car after some time because you simply don't need to keep that information. Nothing happened at the location where you parked your car. There wasn't a crime. You didn't have to remember any particular event. It's just a place you parked your car. You got your car back. You moved on with your life. Where you parked your car that day is completely irrelevant. And as a result, that memory will therefore be more likely to be lost. And what likely is happening is the of the real estate in your brain, the section that had retained that 3-hour memory of where you parked your car simply will get overwritten by new memories coming along because it's simply not needed any longer. Now, how much memory can you store in long-term memory, right? Now we know in sensory memory, we have tens of millions of sensory receptors operating at any one time, but there's really not much in the way of storage in that case because things decay after a second. In short-term memory, you can only hold 7 items. How much memory can you hold in your long-term memory? Well, there's simply no known upper limit. For the oldest people that have been evaluated, for as best that psychologists can actually question them, they do still appear to remember most of the relevant aspects of their life. But when you say it like that, the relevant aspects of their life, the main storyline that they remember and tell over and over again, there's certainly a lot of details, irrelevant events, and so forth that may have occurred to them 80 years prior. And it's difficult to actually evaluate how much of that kind of information is still retained. And so I think there's often a difficult issue, a difficult methodological problem with trying to figure out how much information can be stored in a human brain over the course of their life. One of the things that people talk about in a purely hypothetical sense is that if typically now people live to roughly 70 or 80 years of age, approximately, but they don't seem to have completely forgotten their entire life from the point where they were 20 years old or younger, right? It's not like for every new memory that they put in their brain at age 80, they have to forget something from their teen years, right? That doesn't seem to be a process. Nobody witnesses that sort of thing. The one question is if genetic engineering, very possibly, is kind of somewhat of a science fiction hypothetical, if in, let's say, 50 years from now, genetic engineering starts making people healthier and they live to be 200 years of age, could it be possible that you actually start to see that people, when they reach 200 years of age, actually do start forgetting the earlier part of their life simply because they've been alive for 200 years and their brain is literally maxed out with information. So to put in a new memory for your 200th birthday, you have to forget that your first child was born on a Tuesday. Or that you went to your junior prom or some other event from long ago that's much less relevant any longer because you're 200 years of age. That is a purely hypothetical issue. There are no facts. People just deal with it in a very science fiction-y manner, but it is a serious question, one that simply can't be can't be answered at the current time. Now, the next iClicker question we have to take a look at here is this. Which of the following statements is false? All right, now we have a series of 5 separate general comments about memory. One of them is false. Go ahead and pause the video if you want, and I'll give you the answer in a moment. Okay, the answer there that is definitely false is C. Experiencing an event eliminates the chance of faulty recall. That simply never happens. There is no chance at all under any circumstance with any person that there is no chance of faulty recall. In the information processing model, which is essentially the best model that we have for memory at the current time, information is lost in all 3 sections: sensory, short, and long-term memory. Therefore, answer C has to be completely wrong. There are other parts here that we haven't been talking about too much in this particular chapter, but they do carry back to other chapters that we've been through, such as in A. The hippocampus is part of the memory system. That was definitely a neuroscience chapter issue. B, strong emotions increase the chance of memory storage. That was also a neuroscience chapter issue, and it also came back to us when we talked about subliminal messages in the sensation and perception chapter. Memories related to plasticity. That was actually a neuroscience chapter issue, and it has been a continuing issue in this particular chapter. And the idea that all memories decay over time was very much a part of the story when I covered the information processing model, where I said, in maybe the most dramatic sense that I can, but it being completely accurate, and that is, you are forgetting all parts of your life at all times continually, and you're just replenishing memories into your brain as time goes by, but you are forgetting everything at all times. Now, what kinds of things are actually known about storage? There are a variety of things that are known. Most of them, at least in terms of the biological bases for memory, tend to be fairly complicated, and we simply don't deal with them in general psychology classes because they tend to be nothing more than strings of biochemical pathways that start with genetics, turn into proteins, and the proteins not being memories themselves, but rather substances that will cause new growth in a cell for new dendritic spines, new axonic spines, or the reduction of axonic or dendritic connections to other cells. Those tend to be very specific biochemical pathways, not really worth talking about in this particular class, more so for a class specifically on brain science. But the story, the underlying biological story, though, is still rather fractured. There's a variety of things that are known, but gaps in knowledge between the stories. And I have given you kind of a general storyline since the beginning of the semester, at least since the neuroscience chapter. And that is, when you experience events, the receptors in your eyes and ear and so forth generate action potentials. Those are the only ways to feed information into your brain. When they reach your brain, they get processed. The processing takes place, adjusts some of the pathways in your brain. The adjusted pathways in your brain are essentially the memories. And so you have, if you take a look at these, the list here on the bottom of the slide, proposed neurocircuitry. And that's going to be things like your memory for visual events are going to be stored in your occipital lobe, and of course, those memories are going to be stored in circuit pathways, general brain areas. The idea that all of your memories for sound are going to be in your auditory lobes, which are going to be your temporal lobes. All memories for touch the feeling of anything simply will reside in your parietal lobe and no other place. Every memory for a motor behavior, like a new dance step, or your ability to ride a two-wheeled bicycle or to do any kind of coordinated action, will be stored in the single lobe that is dedicated to motor output, and that is your frontal lobe. There are aspects of messenger RNA, which we won't talk about specifically, but the production of messenger RNA to make proteins that will then modify the function of the cell is one of a key underlying biological principles to the formation of memory. In fact, new memories always have to activate genes to generate proteins to modify the cells themselves. Ultimately, it's going to be the modification of the cell that will help establish the memory. The biochemical principles underneath either occur or they don't occur. And as I've kind of made mention of those things earlier in the semester, if they occur, then you have a memory. If they don't occur, then there is no memory. And in cases that like that, where there's simply no memory in an organism, that organism's going to die. And so that's not going to be something seen today because all of those individuals are simply wiped out of the gene pool millions of years ago. So there are different neurotransmitters depending upon where in the brain you actually look. Of course, the role of neuroplasticity is a pervasive issue for every single chapter in this textbook. There's no way to get away from neuroplasticity. It affects everything, and it's important for all processes. Now, the things that are best well known, at least if we could talk about in a more general sense, are these. The hippocampus helps file and retrieve memories. Now, you may remember the hippocampus as the cork on the end of the ram's horn of the limbic system. And as a reminder to you, I described how the limbic system starts in the very center of your brain near your thalamus and loops around in both the left and right hemispheres, kind of like a ram's horn. And at the very end of the horn, the very tip, if you had placed a cork on the end of each of those horns, that cork would essentially be the hippocampus. And the hippocampus is directly related to the filing and retrieval of memories. It's about as close to a central processing center for memories that you can talk about, but it is not the entire story. Because, as I've already mentioned, memories for different types of sensory experiences will reside in different areas of your brain. The hippocampus holds the pathway to those separate areas, and as a result, it can file and retrieve the memories, establish where they are, so when they're needed, the hippocampus is of critical importance to be able to obtain those memories. It is probably the most integrated brain area, and in fact, within the past 10 years, it has been found to be the only area of your brain that generates its own stem cells. That is a highly important idea because stem cells are undifferentiated cells that can turn into anything. And generally, the appearance of stem cells dissipate at a very young time during development. To find stem cells in the hippocampus indicates that with all the experiences you have all day long, day after day, year after year, the hippocampus has to become more and more complicated, more and more integrated, and therefore there's actually a need for stem cells in the hippocampus specifically. So it actually kind of buttresses the idea that the hippocampus is very much related to the filing and retrieval of memories. Stronger emotions form stronger memories. That was an issue we talked about with respect to repressed memories and also the subliminal information business. The straightforward rule that I gave you before in the sensation and perception chapter is that weak stimuli produce weak memories and strong stimuli produce strong memories. And under those circumstances, you always find that stronger memories are formed from stronger emotional events. And when you go to an extreme, you begin to get into the realm of post-traumatic stress disorder, that is PTSD. That process occurs largely for one special reason, not just the activity of the hippocampus, but of the amygdala as well. We talked about PTSD back in the neuroscience chapter, and the primary underlying biological principle that occurs is this. The hippocampus, which is at the very end of the limbic system, is also right next to the amygdala. And the amygdala, you should remember as one of the primary areas of the brain that we talked about, controls fear and aggression. And when the areas for fear and aggression are activated and that being right next to the hippocampus, it is easier for the amygdala and the hippocampus to become linked together through their neural connections. And there is a biological proclivity to form memories for anything that is related to fear and aggression as opposed to, for example, reward. You may remember that the reward section in the limbic system is actually along the top of the horn, the top of the limbic ram's horn. And that is quite a distance from the location from where the hippocampus is, which is at the end of the ram's horn. Because the amygdala is next to the hippocampus, they simply form connections easier, and therefore there is a biological proclivity to form any kind of memory related to fear and aggression. And that becomes part of, not the complete story for certain, but part of the significant aspect of post-traumatic stress disorder always being related to things like battlefield experiences, being a victim of a violent crime, being a victim of torture, being possibly in a severe car accident, anything that will involve fear and aggression, those memories tend to be formed very, very strongly. Now, any area of the brain that gets used more and more tends to increase the number of synaptic connections in those areas. There's a lot of basic research on this kind of process with respect to animals, especially laboratory animals that you can house singly or in groups. Animals that are housed singly tend to, singly by themselves, tend to have fewer synaptic connections in their cortex as compared with animals that are housed together where there's more social activity and possibly other objects to play with in the environment. After research on non-humans was actually conducted, there was an expansion of the research into humans. And how you do this with people is to do brain scanning. Take a person who, let's say, does not play a musical instrument. Scan their brain on the day before they start playing the musical instrument and evaluate the degree of a cortex that's related to hand control. And then give them the instrument, have them practice every day over the course of about 3 months, and then come back and brain scan them again to evaluate the degree of activity in the primary motor cortex, specifically in the area that controls their hands. And you'll actually find a great deal more activity in those sections simply as a result of practicing the instrument over the course of 3 months. Now remember, this does not mean that there's more neurons in those areas. The number of neurons is held constant. What has actually happened is the number of synaptic connections is increased. So as we were talking about earlier, with messenger RNA and genetics and the proteins that are generated inside of a cell, more dendrites grow, more axonic branches grow, and so there are more connections between the cells in these areas of the brain, so that there are actually a greater number of synapses and therefore more electrical activity traveling along the pathway that controls the hand as a result of its use in practice for a musical instrument over the course of 3 months. And that process, although seen with musical instruments, has also been expanded to be seen in other ways as well, such as you might imagine, math professors certainly have more activity in the areas of the brain that control mathematical reasoning than do most of the rest of us. Athletes, college athletes like some of you, or even professional athletes, tend to have much more activity in their cerebellum. You may remember the cerebellum as the section in the lower back portion of your brain that has a primary role in controlling coordination. And certainly that would be true for gymnasts or anybody that does very coordinated activity in that manner. There'd be a lot more activity in the cerebellum. So to find this, remember it's not the number of cells, but actually the number of connections in those areas that help form these memories. But of course, we keep talking about how these memories become formed. There are, though, ways in which these processes wind up getting reduced. And the basic rule, remember, that I gave you is that stronger emotions form stronger memories. And that is absolutely correct. However, one thing you have to remember is that with respect to you, a biological organism, it is always possible to exceed the normal parameters in which your systems operate. And when you fall outside of those ranges, you wind up corrupting the system. And of course, this is true with everything, right? Yeah, a plant needs water. If you give it too much water, you'll wind up killing it. A plant needs sunlight. You give it too much sunlight, they'll wind up dying. You need friendship as a gregarious human being, but if you're never have any downtime, never have any time by yourself, you'll probably start to develop anxiety. This is a common principle with all living things. There's a normal operating range in which things typically behave, and outside that range, you oftentimes get corrupted behavior. So what I'm going to do here is I'm going to show you a 1-minute clip from a 7-minute video I will show you in the Psychological Disorders chapter regarding an interview with Jeffrey Dahmer, who was a serial killer from the late 80s, early 90s. Now, at this interview, Jeffrey Dahmer has already been caught by the police. He's being interviewed by a fellow named Stone Phillips, and the video is describing how Dahmer is not trying to avoid his responsibility for committing murders, but of the many murders that he actually committed, some of them he simply doesn't remember. He knows he had to have committed the murders, and he admits it, but he doesn't remember it. And the particular murders that he tends not to remember tend to be ones where he actually beat somebody to death with his own hands. And as you might imagine, that's probably an intense emotional experience. And as a result, Dahmer seems to have exceeded that emotional capacity during the time of the murder, so that his memory system became corrupted, and then he later on simply had no memory of the murder itself.
But Jeffrey says in 1984, while living here at his grandmother's house in Milwaukee, his violent compulsions consumed him once again. One night, cruising these bars in downtown Milwaukee, he met a young man and took him to this hotel.
I had put some sleeping pills in his drink to render him unconscious, and was just going to spend the night with him. When I woke up in the morning, My forearms were bruised, and his chest was bruised, and blood was coming out of his mouth. He was hanging over the side of the bed, and I have no memory of beating him to death, but I must have. And that's when it all started again.
And once it started again, you found it impossible to stop.
Right, that's when the obsession went into full swing.
This sort of thing actually is reasonably common for people in extreme situations, even for car accidents, for example, where a person's driving up a street, and when they reach the corner, they just avoid getting into a horrible car accident. Okay, so to be clear, in this hypothetical scenario, the person drives up the street, reaches the corner, they are not in a car accident, but they just miss being in it, and they become terribly afraid at that moment. So they haven't hit their head, nothing has happened otherwise. This is just something you would refer to as emotional trauma. When if that person remains there at the crash site and later on the police show up and they say, can you tell us what you saw? The person may actually have no memory of the event at all. They will remember having driven up the street, and the closer and closer they get to the corner, the less and less clearly they'll remember anything about driving to the corner until finally they just won't have a memory of the crash site at all. They'll just know that they got there and they were shook up and didn't drive off when the crash was over. So it is a process in which emotional trauma, okay, to make this real clear, separate from physical trauma to the head, just emotional trauma itself could cause a disruption in the formation of a memory. But be very aware, though, this is a lost memory. Okay, this is not a scenario where we're bringing back repressed memories. There's not some hidden component of the memory that's hiding in your brain that's going to pop out later under hypnosis. Those are all things that we've talked about before that simply don't have very good support for them. This is just a lost memory. The information is gone, and it's not coming back.